Implementation is the final frontier for us, sort of. We started our journey when we talked about requirement specifications. This is viewing the system as a black box. We figured out what the system should be able to do without getting into details of how it was done. Then we proceeded to software analysis, in which case we would look for what was needed to be inside the black box in order to make it work, specifying those components. We viewed object-oriented analysis, so we talked about the classes of objects that needed to be implemented inside the system. The design takes the analysis model and describes how the code will work. Finally, we're up to coding now, or implementation as I'm going to refer to it, where we actually have to turn the design into code. There are two forms of implementation. One is actual programming, using some programming language to actually handcraft the lines of code. The other is actually avoiding handcrafting lines of code, and that is accomplished by reusing components and sort of gluing components together. We're going to talk about each of these separately. In our discussion of programming, I'm going to talk about features of programming languages that help us in this job, using languages in an effective way to promote better software engineering. Talk about, this is sort of an outline. We're going to talk about the purpose of languages, then how users of programming languages, the design of languages, classification of languages, complexity, attributes. And then we'll conclude with 2 pages that I've copied out of a book by Kernahan and Ploggers, a real old book. I think a lot of their advice is pertinent even today. And you'll have a little writing exercise you'll have to do based on those do's and don'ts, and plus any other information you find in the literature. Okay, we'll start by talking about languages, purposes of languages. The 3 main purposes of languages. One is, the obvious purpose is to write code, right? The obvious purpose of a programming language is to write lines of code to control the computer. Right? So let's dispense with that right away. But the other main purposes of a good programming language is, first of all, design. There was a man, he was a psycholinguist that lived probably 60 years ago or so. He did a lot of research on the use of language, and his conjecture was that the way people, societies, cultures, the way they solve problems is heavily influenced by the language that they speak. You may turn that around to say, well, the language that we use is sort of influenced by the problems we have to solve. But his idea was that the different cultures speak different languages and enables them to solve problems that they're facing, and different cultures will solve the same problem in different ways. And his idea was it was based on language. Well, if he had done his work nowadays, since we've had programming languages, I think it would serve as a much better example of his theory. If you think about the language, the programming language that you're most familiar with, perhaps it's the one you learned first. I suspect that the way you approach the design of a program is heavily influenced by that language. You tend to think in terms of some particular language. And over the years, I've taught many different programming languages, and I can remember having to teach people more object-oriented languages. These people had grown up many years of programming in languages that were not object-oriented, like Fortran programmers and COBOL programmers. And I can attest to the fact that the way they think about the structure of programs, the way they think about software design, is heavily influenced by their language. Fortran, for example. Somebody once said you can write a Fortran program in any language, and that's probably true. The way you think about programming, the way you think about the design of a program is very heavily influenced by the language, the programming language that you use. So given that, languages then, by Worf's conjecture, would say that the language that you use will affect the way you face program design, the way you solve problems. All right, so languages do aid in program design. Better languages, there are better languages for doing program design than others. Okay, so for example, assembler language is not a particularly good language to help think about program design because there's no structure to it. An object-oriented language, on the other hand, would promote the use of object-oriented analysis and design because the concepts are very similar. Languages also aid in program understanding. They help, a good language now will help people to read the program and understand what it's all, what it does, what it's all about. So you can contrast languages based on how well they aid in understanding the program. Once again, assembler is probably not a very good language to aid in understanding the program because it's so low level. And once again, probably a higher level language like Java or C++ or things like that would be better at aiding the understanding of what somebody else has written. And the third thing is program verification. Now, what I mean by this is there's a class of defects that we inject in our software that we used to, that we can't make those mistakes again because the programming language has prevented us from making those mistakes, injecting those defects. Here's a real simple example. In Fortran, the language Fortran, there are no declarations of variables. Variables are sort of implicitly declared just by using them. So you use a variable in an assignment statement, either on the right-hand side or the left-hand side, and the compiler says, just adds that to its symbol table. Every variable name that it sees in the program, it goes into the symbol table, and it's a legal variable. Now, if you accidentally misspell the name of a variable, the compiler simply says, oh, there's a new variable, and it adds it to the symbol table. And so it is possible to have a suppose you write an assignment statement and misspell the name of a variable on the right-hand side of the assignment statement. Compiler says, whoop, new variable, adds it to the symbol table. That variable name never has a value assigned to it, yet it appears in the right-hand side of this assignment statement. And if you don't find that mistake by some inspection or some other tool that examines the program, that variable will have garbage in it or have 0 in it or something, but you'll get unexpected results. Right? That's a mistake. I mean, that's a defect that crops into programs, and if you don't carefully inspect the Fortran program or use other tools to find those kinds of defects, they will lurk in your program. More modern languages that require declarations of variables avoid that problem. You never have those kinds of defects in programs that you write in, say, Java, because you're forced to declare all your variables before you even use them. And so if you mistype the name of a variable, the compiler will detect that. Okay, so that's what I mean by program verification. The programming language syntax and then the compiler that compiles the program it is difficult or impossible to make some of the mistakes that we would make with other languages. So in the history of programming language design, they have added features to programming languages to enable the compiler to sort of check for defects that earlier languages sort of let through. So we can see that we have three main sort of like audiences, user groups, if you will, for the design of a programming language. So if I'm a programming language designer, obviously I will have to design features in my language to support the programmers because they are the main users of the language. However, or the compiler. Right? However, we have two other sort of audiences that we have to keep in mind when we're designing programming languages. This is a lot of based on what we looked at in the previous page. We've got readers. Okay? You have to design, when you're designing your language, you have to keep the readers of the program in mind. Think about this. One person will write a line of code, but there may be, for that one, that one person that wrote the line of code, there may be 5 or 6 people that actually read that line of code, maybe even more. Right? You've got reviewers, you have testers, you have maintainers over the entire lifetime of the software that will have to read the lines of code. So certainly you want to provide facilities in the language to help programmers write the lines of code, but you've got to put a lot of attention in the language design, paying attention to the readers who have to read that line of code, those lines of code, and make sense out of the program. And the third sort of audience or user of the language. I mean, when I'm designing languages, I have to keep the computers in mind also, right? So you want to design a language that will allow the compiler to create efficient object code. There are three aspects of other aspects of language design. Everything seems to come in threes in this module. Okay, language design. One of the things, now the two of the things are sort of mandatory. The third thing is sort of nice to have. The first two, though, representation and handling of data. So any language is going to have to support features to allow the programmer to represent data types and variables and objects and classes or whatever, and handling of data, all the operations on the data. Okay, so that's obviously what programs do, right? The programs are data plus operations. Also sequencing of statements, some way to tell the order in which things happen. Now this certainly is necessary in an imperative language. There are some declarative languages that don't have the sequencing of statements implicitly in the program, but there's explicitly in the program, there's an implicit sort of ordering given by rules that you specify. But you have to provide some way so the computer can know which operations are performed in what order. The third feature of programming languages is nice to have, but it's not mandatory, and that's segmentation. In other words, you should provide a way in which the programmer can modularize the program into pieces, right? Back in the old days, we may have had segmentation, but programmers didn't do it. Remember when we were talking about modularization? I mean, there was a point in time that programmers didn't modularize their code, and one module would go on for thousands and thousands and thousands of lines of code. It is necessary these days in order to make your programs more understandable for you to be able to segment them. So a decent language these days should provide some mechanism for segmenting the program and breaking it into pieces, either procedures and functions, or classes, or modules, or packages, or some unit of modularization, so that you can make understandable pieces and put those pieces together in controlled ways. We could classify programming languages. Here's some classifications. Right. Commercial languages, the most common one there is COBOL, I guess, right? Scientific languages, probably the most important language from a scientific standpoint was Fortran, and it's still being used today, even though it's probably one of the it is the oldest high-level language around. Command languages. Yeah, these are languages used for like operating system commands. Yeah. DOS would be a good example of a command language. Interactive languages allow you to program interaction with the user at some user interface. Scripting languages, VB would be a good example of a scripting language. Procedural versus non-procedural. A procedural language is one in which you specify to the compiler the order in which you want the operations to be performed. A non-procedural language is one where you specify rules, and then at runtime, based on data and based on the state of things, the rules will fire in the order specified by the rules. And you don't have to specify in advance what order the rules will fire in. An example of, most languages are procedural. An example of a non-procedural language is Prolog. If you think about it, a spreadsheet is sort of like a non-procedural language. You just put rules in each of the cells, and then you change a piece of data in one place, and a whole bunch of cells will fire, actually implementing their little functions in some order given by the rules set up by the spreadsheet. An applicative language is one. It's both a style of writing programs as well as there are categories of languages that make it easier to write these applicative programs. An applicative, what the word apply means here is that you have a function that you apply a function to some data, and then the result of that function is applied to another function, and so you actually have you have some function. there we go. Yeah, you got some function on some data. And then they take the result of that function and you apply it to another function. And then you take the result of that function and you apply it to another function, and so forth. And this is called the applicative style of programming. So it's a result of a function being applied as the input to another function, and the result of that is applied to another function. So it's a function of a function of a function of a function of a function. Eventually, there's some data in there. Okay, that is an applicative style of programming, and there are languages that support that. Lisp would be a good example that comes to mind here. Data flow languages are languages that sort of simulate the data flow diagram kind of idea. Object-oriented languages, any language that you can create classes and then create the object instances at runtime. Java, C++, C#, so forth. Those are all object-oriented languages. Real-time languages are languages that support capabilities that are needed for real-time programming. These are being able to have multi-threading or multiple tasks operating concurrently, and then synchronizing those tasks. So allowing them to run concurrently or serializing them. Okay, so all of the facilities for doing all that synchronization stuff, that if their language supports that kind of synchronization, then it's a real-time language. Other languages require that you dip down to the operating system to do any of that synchronization stuff. And those would not be real-time languages. Web server versus web client languages, you're probably familiar with those. And then there are just tons and tons of special purpose languages. We could classify languages based on complexity. And there are various types of complexity. One is complexity of scale, how big the language is. One way of looking at this is, well, how big is the reference manual, or a book teaching you how to program in the language? How thick is that book, right? If it's a very complex language in terms of complexity of scale, then the book that describes the language would be very thick. On the other hand, there are some languages that are very simple, very easy to learn, very thin book, very thin user's manual. Languages in terms of syntax, complexity in terms of syntax. This would be like the size of the formal grammar that is needed to describe the language. Some languages are very simple, not very many productions in the grammar. An example of a really simple language is a simpler language. It's not a very complicated language in terms of syntax at all. So don't think that the simple language is necessarily the best language for doing software engineering. Semantics, that's the meaning of the sentences in the language. Control structures, different kinds of control structures. Right? Some languages have very simple control structures, like one if then else and one loop construct. Other languages have 3 or 4 or 5 different looping constructs and lots of different branching constructs. Types, data types. Okay, the ability to create your own data types would be an extension of the typed languages. Some languages don't have any data types. Some other languages have plenty of data types. Right? Java takes a sort of a middle road, has some built-in data types, but then you can create your own data types through classes. Some languages don't have any data types. An example of that would be Smalltalk. It's an object-oriented language, but there are no built-in data types. Everything in Smalltalk has to be created by creating a class. The ability to declare procedures with parameter lists. Now there have actually been languages that didn't have procedures, and you couldn't do procedure calls, couldn't pass parameters. Some of the early versions of BASIC, for example. Some of you may have actually programmed in some of these really early versions of BASIC that didn't have parameters or procedures and being able to pass parameters. The only way you could do things is with something called a go sub, and you specify a line number and then jump down to that line. You had a return, but you couldn't pass parameters. Scope has to do with scope and block nested structured languages. Scope and visibility, input and output. Some languages are very simple. Other languages, Java, for example, is very simple. It doesn't really provide much input output. It all has to be implemented by the programmer. It's not part of the language. Other languages like Fortran has a very complex built-in input-output mechanism. I used to teach Fortran, and we would probably spend 1/4 of the entire semester talking about the input-output facilities of Fortran. It was so complicated. The ability to handle exceptions and to declare exceptions, to be able to catch exceptions, to be able to handle the exceptions, propagate the exceptions, all that stuff. Some languages have that ability. Other languages make it optional. Some languages make it required. Java makes exception handling required, to the chagrin of a lot of programmers because it gets in their way. But it also makes for very safe programming. The ability to have parallelism, to be able to have different parts of your program running concurrently, asynchronously, and then being able to synchronize those. That's an aspect of language complexity, but also very language power, I guess. Different attributes of languages. I just picked a couple here. One is should the language provide strong data typing? Good examples of languages that have strong typing. Now, what I mean by strong typing is every variable in the program will have a data type, and the compiler will check every time you use that variable. The compiler will check to make sure that you're using it appropriately, that you don't mix variables of different types in an expression. And passing parameters, the parameters are matched on both the call and the sender and the receiver of the message. Ada and Java are strongly typed languages. Smalltalk is extremely weak typing. There are no, as I said earlier, there's no data types in Smalltalk. Everything is done with objects, and really the only checking that the compiler does is that that I have a variable and it's pointing to some object. So I can combine variables that point to different classes of objects, different objects of different classes in the same expression, and it's actually happened. The checking for typing is done at runtime rather than at compile time. Extendability, being able to extend the language. Remember we talked about procedural abstraction and data abstraction before. Being able to create your own data types, being able to create your own procedures and functions. Overloading is something, it's related to extendability, but it's not exactly the same. Overloading means that you have multiple, say multiple functions in a class with the same name, different parameter lists that do related kinds of things, but using different parameter lists. Extensibility is the ability to actually modify the syntax of the language in a way. There are languages that allow the programmer to actually modify the syntax of the language through changing the compiler. And so the first part of your program defines the language, and then the rest of your program is written in this new language that you just invented. The language that comes to mind here is, one of them is called Forth, F-O-R-T-H. I did some work in that a number of years ago, and it was kind of fun because you got to make up your own language. The ability to have separate compilation, the whole idea of being able to separately compile or recompile components, is that if I have a huge program and I want to modify something, I just need to be able to should need to be able to just recompile that one piece and then integrate all the results together. The old languages, Fortran, COBOL, and so forth, were all built along this separate compilation idea. The problem with the separate compilation is when you're compiling one module in, say, Fortran, the compiler doesn't know any of the other modules. And so if this module I'm compiling makes references to some other, like a function call to some other module, the compiler can't check the interface, can't make sure that the right parameters, data types are being passed, the right number of parameters, and so forth. It can't check across the interfaces between modules, and this is where an awful lot of the problems would come up in the old Fortran programs. The opposite, the way that you'd handle that, and the way they handle that with, say, Pascal, the first version of Pascal that came out, was they made, in order to check across the interfaces, it made you recompile the entire program, all the pieces, as one giant compilation. Even if you changed just one little line in one little module, you had to recompile the whole thing in order for the compiler to check the interfaces. Of course, we've solved that problem nowadays, right, with C and C++ and Smalltalk and Ada and Java, and all those languages now have the ability for the compiler to check the interfaces, right? Because in order to compile a reference to a module, that module must have been compiled, and the compiler keeps track of the interface information, so that when you compile some a module that uses that module, it can look up the interface information to make sure that you're invoking things properly. Now, these next 2 pages I'm not going to read. This is your reading assignment for the little writing exercise I'd like you to do. But these are just, now the book has do's and don'ts of programming. The original book is by Kernahan and Plagger. It's called The Elements of Programming Style. You notice the date on there, 1974. It's an old book. A lot of these things that they talk about are still valuable guidance today. And I didn't copy everything out of the book. I mean, they got lots of rules for do's and don'ts. These are just a subset of them. Their book came out in various editions. This is one of the earliest editions. This happens to be the one that I have in my bookshelf from my graduate school days. The name of the book is interesting, The Elements of Programming Style. The format of the book, the style of writing the book, mirrors another book. The name of that book is The Elements of Style by Strunk and White, which you might look up in Google that one. The Elements of Style by Strunk and White. In their book, what they're talking about is the style of writing in English, and they talk about English grammar, rules for using English in a written format. And so they talk about do's and don'ts. And in Strunk and White's book, they put a rule in a box, and then they show examples of using the rule properly and examples of breaking the rule, mistakes that people make in misusing. And so in Kernahan and Plagger's book, they follow the same style as Strunk and White. They put a rule in a box, and then they show examples of software that uses the rule properly, and then examples of software that violate the rules. And so that's kind of an interesting way of presenting style. And since they came out with their book, Elements of Programming Style, you see lots of books using the same kind of name. Elements of C programming style, the Elements of Pascal programming style, the Elements of COBOL programming style. You probably find a book with that same kind of name for almost every language that's around. And if it's not, there's an opportunity to write a book. So here you have a little writing exercise, just to go out and to the internet and look for some information about do's and don'ts for programming.